So, some nodes you may find big numbers like 1298 is the combinational controllability CC0. So, let us say CC0 of some wire here, let us call it as W, is 1298. Similarly, combinational controllability 1 of some other number, let us say U, maybe 2925. So, if you have such big numbers, that means this guy is very difficult to control to 0 or difficult to control to 1. Similarly, observability, we may get some big number like 4925. It is very difficult to observe this guy. Which is the reason why that combinational ATPG may take a long time. Okay. The method I told you earlier about calculating the combinational controllability, observability, etc. This method is called SCOAP. SCOAP is the algorithm that can calculate these values, combinational 0 controllability, combinational 1 controllability and combinational observability. This was given by Vishwani Agarwal. So, Vishwani Agarwal and Sharat Seth. So, they have published a paper which describes how to calculate the combinational controllability, 0 controllability and combinational 1 controllability. It is fairly straightforward, okay. And when you use this algorithm, if you notice that some lines are very difficult to control to 0, okay. So, let us say there is one line like this, let us say this is W and it is very hard to control it to 0. The scope number for the CC0 is very high. So, a little bit of we can modify the circuit. If you are allowed to modify the circuit, what you could do is you could introduce an AND gate here, okay, and you can give a control line, okay. So, originally W was directly available like this, but now it has been modified. So, if I make this 1, this W has not changed, the functionality of the circuit has not changed. So, 1 dot the old W is W only, but if I change it to 0, then this suddenly becomes 0. So, I can control this to 0 very easily. So, for the purpose of testing, if I want to improve the 0 controllability of this line, I can give an additional input. Okay. Similarly, if I have a wire which is very difficult to control to 1, I can always put a OR gate here. And if I want to if this is 0, no change, the original circuit remains as it is. But during testing, if I want to control this line to 1, just make this 1. Because remember, during testing we do not care about the functionality of the circuit, we want to somehow address the stuck at faults. So, we are not really interested in the functionality of the circuit so much. So, let me illustrate this a little bit. Suppose I had some circuit, So, there is a complex circuit like this, okay, and we are finding that it is very difficult to control this line to 0, right, and because of which our ATPG algorithms take long time, okay, because they try to make it 0, but by PODEM algorithm will try to make this 0 by back propagating, it is taking too long. So, what is the recommendation? The recommendation is you just modify the circuit and introduce a AND gate here and make this the primary output. So, we added an extra AND gate. If I make this control line to 1, then the circuit's functionality has not changed. Okay. So, this wire has the same, so if this value is x, x dot 1 is x only. But during testing, if I want to somehow make this 0, it is very easy. I can make x equal to 0 and the algorithm will not realize. See, the test algorithm does not understand the functionality. The DE algorithm or PODEM, they do not understand what the function is of the circuit. They do not care whether it is an error correction and detection circuit or some arithmetic circuit. So, they are just blindly looking at it as a gate level circuit. So, when they see this, when PODEM when PODEM tries to put a 0 here, if it follows this path, it is very easy, just put a 0 here and it will. Similarly, if I wanted to improve the controllability of one controllability of a line here, I will modify this guy and by putting an OR gate. Okay. If I put y equal to 1, I can increase the y 1 controllability. What is the price I am paying for this? Okay. It is not coming free of cost. See, the 2 gates or a few gates that I introduce may not take much area. Today we are not worried about the gate delay, I am sorry, the gates per se, but they are going to introduce some delay. Okay, so, there is some delay and that may be something undesirable. Okay. And they may take a little bit of power, again that may not be such a big deal, right. So, whenever we propose anything like this, people ask us what is the power increase that you are going to see, what is the performance deterioration that you will face, and what is the area penalty that you will incur. So, there is some area penalty, there is a little bit of power penalty, but what may really be something that people are going to complain about is it is going to increase the performance. And last but not the least, you may end up with an extra pin. See, in a circuit, these are the pins, right, these are the IOs. So, if you are demanding an extra IO pin for the sake of controllability and observability, extra pin, this is a biggest concern. So, this is something that people will raise their eyebrows. Performance, this may not be such a big deal, area penalty and power may not be such a big deal. Okay. So, when you modify a circuit, so modifying a circuit for improving the test performance. Okay. This is known as design for test. So, we are changing the circuit a little bit, okay, because it is going to help the test. By adding these extra gates, we are improving the controllability, and as a result our test generation algorithms will work fast, right, and our coverage may improve a little bit, right. Earlier our algorithms used to abort certain faults. Now, we did a controllability analysis using SCOAP, we did an observability analysis using SCOAP, and wherever one controllability is very high or rather it is very poor, okay, high number of when the SCOAP controllability number is very high, that means it is a very poor controllability. So, we found that the CC0 is very high. So, we wanted to improve that, so we added an AND gate. So, this is called as a test point. So, test point is this AND gate etc., that we add. Okay. Similarly, the OR gate that we added is a test point. So, it is called as a test point insertion. So, test point insertion is a simple design for test technique. And like I said, it comes with certain penalty. Okay, it comes with the penalty of some extra power, some extra area, some extra delay along that gate, and finally, maybe you are going to ask for an extra pin. So, for pins, what they will do is they will multiplex this pin with some other pin. They will say, do not worry, I am not going to ask you for an extra pin, I am going to multiplex the pin with many pins, right. So, pin multiplexing is used, so that people will not scold you for asking for another pin. Okay. If the observability is very poor, okay, if there is a wire whose observability is really terrible, then one simple way is just bring out the wire as an extra output. Okay. Just make that an output pin. Okay. Normally, it is not an output pin. Okay. So, observability can be increased by making an internal line a primary output. See, normally that there is no advantage in observing that line directly. Okay. So, this is similar to how you may have debugged C programs. Okay. See, when you did a C program, right, there may be many variables, int, etc., etc. Normally, at the end, what is the output that you want? Maybe you only want the actual things, like maybe sorted out, numbers have to be given, they have to be printed, etc. But when you want to debug, you also place additional print statements, isn't it? Your program is not working, it is going into some sort of a loop. Okay. So, in program debugging, what we do is at some point we will say printf, okay, variable z equal to this z may not be such an important variable, nobody cares what this z is, but the value it prints may give you a clue as to what is going on. If you expected it to become equal to some value and you find that it is not happening, then you know that the bug is in that z, right. So, this is how you are improving the controllability, I am sorry, observability. So, we have increased the observability for z. When you write a program, it is not so big deal, right. I mean, putting a print statement to print the value of z is not such a big deal, right. Of course, when you send the final program, you should remove that print statement. Okay. When you have debugged it finally, you may want to make this a comment, right. But when debugging, you will like to leave that print statement as it is. Okay. So, in a way, that is what is happening in the observability improvement, right. That particular wire is not useful during the actual function, but during debugging it is useful, during testing it is useful. In the same way, in writing a program, see, maybe there is a very complicated there is a function that you have defined some here. Okay. Let us say we have defined maybe some function for calculating sin theta. And sin theta is called somewhere here. Okay. This x is being passed on as theta. This x itself comes from some other complicated function. Get angle. So, that it is like having get angle gets me x and that goes to sin. But how do I want to know whether sin itself is working correctly or not, or whether the bug is with get angle. Okay. Then what I want is, I want directly sin to get some value. Okay. So, I can put a multiplexer of some kind. Sorry. Sorry. So, during debugging, I will directly give some value. During actual test operation, get angle will produce a value. So, what I can do is, if debug then x is equal to some value. See, I am overwriting the value that get angle gives me, so that if it works correctly with the theta that I am providing, that means the problem is with get angle. If it does not work even with the correct angle, that means I suspect the the sin function. Okay. So, that is how we can sort of debug and the same idea can be extended to hardware also. That is what we are doing by improving the control. This is improving controllability, and this is improving observability. The printf statements are improving the controllability, I am sorry, observability, and these kind of assignment statements are improving the controllability. Is that okay? So, when the fault coverage becomes very bad, okay, if fault coverage is less than 96 or whatever, suppose your company is asking you to get you 96% coverage and you are not getting 96% coverage, you have to start looking at how to improve the coverage, right. So, you can run the controllability analysis, you can run observability analysis and find that, oh, there are some nodes which are very poorly controllable or very poorly observable, then see whether we can add test points. Okay, adding test points may improve the coverage. So, it depends on how many test points you add. If you add too many test points, people will not be very happy because you are asking for too many pins and too many performance may get degraded. Okay. So, that is a little bit of an optimization problem. You have to add the right test points, so that so in all this testing etc., you will find a lot of optimization problems. Okay. These are hard optimization problems. It is not easy to find a good algorithm to solve this optimization problem. You have to use some sort of heuristics. Okay. So, one heuristic could be run the SCOAP algorithm and find where the observabilities are very high, and start one by one. First select one test point and see how much it improves, and then try another one. Okay. You could try that kind of a approach. Okay. So, that is about improving. So, you must all understand what is meant by design for test. Okay. This is the first time I have used that terminology today. Okay. It is a very important thing, DFT. Design for test. Okay. So, means ask for small changes in the design to improve the test. When I say improve the test, it may mean make better coverage, or improve the coverage. Okay. Or test run times. Okay. Your tests will run faster. So, these could be the goals of design for test. Okay. All right.